The classical three-body problem is famous for its unpredictability. Introduce three masses into a gravitational system, and the math dissolves into chaos. But the problem isn't the math. It is the assumption that we are looking at discrete objects. If we reframe these bodies as compression nodes within oscillating waveforms, the chaos resolves into an interference pattern of overlapping fields. This breakdown isn't isolated to orbital mechanics. In the quantum realm, the standard model relies on 19 arbitrary parameters, mass ratios, and couplings. These values must be manually measured and plugged into equations because the theory itself cannot predict them. These are two symptoms of the exact same problem. Standard physics operates using Euclidean trajectory tracking and real number algebra. These mathematical tools were designed to describe isolated objects and linear forces. They fail when applied to domains governed by deeply coupled, nonlinear phase feedback. Classical chaos and arbitrary quantum parameters both stem from treating physics as Euclidean object mechanics rather than transductive phase geometry. The oscillatory dynamics transductive bridging theorem, or ODTBT, proposes a structural solution. The universe operates entirely through transductive phase geometry. ODTBT treats the 19 parameters of the standard model as shadows, low-dimensional projections of specific phase positions within a larger structure. Every measurement we take and every value we record exists strictly within a two-dimensional observable projection space. In ODTBT, this is identified as the O2 layer. The origin of these values lies beneath the projection. The values are generated by a 12-dimensional recursive manifold known as the S12 substrate. Deriving these constants from first principles requires abandoning the O2 real number coordinate system entirely. We have to execute an inverse coordinate transformation, mapping the shadows backward to calculate the exact geometry of the S12 substrate that is casting them. To execute that transformation, we first have to map the complete ODTBT state. That state is a 12-dimensional fiber bundle that dictates how and when physical systems bifurcate and stabilize. This diagram isolates the S12 architecture. The top S5 geometric bulk uses 5 coordinates mapping phase strains. Beneath it, the SU2 spinor fiber encodes scalar and spinor branching. The base substrate layer tracks parameters like lock potential, the source of mass, and observer phase alignment. Together, this 12-dimensional architecture provides the complete topological blueprint. It structurally guarantees the existence of both the observable particle states and the hidden recursive mechanics driving them. Accessing this 12-dimensional reality presents an immediate problem. Every piece of standard physics measurement apparatus operates exclusively within the constrained, two-dimensional O2 projection layer. This rendering illustrates the boundary. The luminous figure represents the observer, whose phase alignment acts as a projection operator, collapsing 12 dimensions of geometry into 2. The standard model's parameters map onto this collapse, becoming numerical artifacts of a high-dimensional reality squeezed flat. This collapse explains the persistent triac structure found throughout the standard model: 3 generations of fermions, 3 color charges, 3 force couplings. That trinity is the O2 shadow cast by a 4-node quadratic substrate. We see 3 active nodes. The 4th is the hidden field source itself. The standard model is a description of the O2 projection. It isn't incorrect. It is simply structurally blind to 10 of the 12 active dimensions governing the system. Proving this requires empirical validation. In Phase 1 and 2 of the ODTBT computational program, independent researcher John Sermont investigated whether pure theta-60 icosahedral geometry could predict physical reality. The scope was exhaustive. 136 pure geometric candidate expressions were generated and blindly tested against 16 recognized physical constants from the NIST database. This histogram tracks that blind comparison, returning an explicit null result with 0 natural matches. The closest fit for the fine structure constant achieved a tight error margin, but required an unacceptable mathematical complexity of 8 distinct parameters to force the fit. Sermont identified this null result as a structural finding. Because 136 permutations of icosahedral geometry failed to match NIST data, the derivation root cannot be a simple spatial coincidence. It identifies a grammar mismatch. you cannot recover a substrate value by comparing two different projections of it. By eliminating the possibility of simple geometric coincidences, the phase 2 result moves the derivation exclusively into substrate phase coordinates. Phase 3 implements the correct inverse projection. It converts the real number constants into their native theta phase positions. The fine structure constant alpha becomes the sine of its designated theta angle. This visualization models the theta recursive harmonic conic. The colored nodes are the physical constants, and their spacing is dictated by an exact rapidity coordinate recursion chain. Each subsequent angle equals -1/2 of the previous angle. The entire particle mass hierarchy is dictated by a single anchor point on this conic, the electron baseline depth, known mathematically as n equals 3. At this specific depth, a rare arithmetic anomaly occurs. The ratio 455/48 approaches 3 pi, with a deviation of exactly 0.054 radians. That precise fractional offset forces the resulting sine wave amplitude down to near zero. Because of this extreme denominator suppression, particle mass ratios are not random free parameters. They are exact algebraic necessities enforced by this geometric anomaly. Taking this theoretical model to exact calculation requires the Euler-Lagrange framework. It serves as the necessary mathematical tool for isolating and calculating minimal zero-dimensional void-locked configurations. Within this conceptual diagram, observe the golden nodes housed within the lower cone. The lock potential directly evaluates particle mass configurations based on that precise theta 60 icosahedral symmetry. By executing that calculation, the geometry natively derives the precise proton-to-electron mass ratio. It achieves the correct measurement without invoking a single free parameter. The transition from point mass trajectories to topological standing waves removes the need for arbitrary inputs, as the values emerge from the wave geometry itself. The chaotic divergence of 3 orbiting bodies and the arbitrary mass values of subatomic particles appear to be unrelated phenomena, yet they share a singular, unifying resolution. Finding that resolution requires shifting our focus away from the real number observable readouts and toward the transductive phase geometry of the 12-dimensional fiber bundle. The standard model remains the most accurate map of the O2 projection mankind will ever create. ODTBT serves a different purpose. It provides the structural map of the projector itself. The shift from measuring the 2-dimensional shadows to mapping the 12-dimensional substrate provides the first principles derivation of physical constants.